Okay. Hi. Good evening, everyone. Welcome to week 6 problem solving session. Okay. Of linear algebra through geometry and PTL course. My name is Bhabhi Deeprai. I'm a PMRS scholar from IIT Madras. So, as always, our classes are held on Tuesdays, 6 p.m. to 8 p.m. Okay, where we'll just demonstrate some problems and how to solve them. Okay. So, without further ado, let's just begin with this week's content. So this week's content consists of mainly two parts. Okay. So as we saw in the beginning of last week, the contents we are focused on is 3D, 3 dimensions instead of 2 dimensions. So what are the contents? There are two major focuses. The first one is linear transformations in 3 dimensions. Okay, this is the first one, and the second one is the effect of eigenvalues and eigenvectors in 3D. So there's a lot to cover in today's session. So, but what I thought was it would be better if I combine both of these and then present questions to get a better understanding of what is the geometric effect of linear transformations and eigenvalues, eigenvectors, and so on. Okay, so I've designed the questions in the same manner. So just two things to note. Okay, just two things I want to slightly recap. Okay, just take a minute. So the first thing is, what is linear transformation? Okay, what is a linear transformation? It is a transformation that can be represented as a matrix multiplication. Matrix multiplication of your vector. Okay, to your vector. And what do you mean by matrix multiplication of a vector? Well, a matrix multiplication will take your components A, B, C and choose suitably, okay, whether how much of A you want, how much of B you want, and how much of C you want. So if you want to do this, you need to say I want something like, one part of A, 2 part of B, and 1 part of C. Okay, and when you multiply this, you get this. So what you get by matrix multiplication is what is called a linear combination. Okay, and this type of the vector that you obtain by performing linear combinations is what is called a linear transformation. Okay, and so on. Great. So now that we have that out of the way, the next thing is so of course, and if you represent it graphically, you will always see that it pushes vectors into different places. It may change the direction, it may change the length of the vector. Okay, it may reflect it across a plane, across a line, it may rotate it across an axis, and so on. Okay, now what are eigenvalues?
Yeah, I have a query here. Changing the direction possible through the linear transformation, because when we get the linear combination, then can we change the direction also?
So we can, right? We looked at what are called these skew, not skew, shear matrices. No, that is an example. Shear matrix. Okay, so what you want is, if you have a vector which looks like this, okay, AB, what you want to do is you want to keep B as the same. You want to keep the B component same, but you want to shift the A component like this. Okay, by some K factor. Okay, so then what you can do is you can multiply A by K and B by 0 and this by 1. So what you get here? You get KA and here you get B. Right. So if you plot it, it will look like this. No? Originally the vector was pointing in this direction, and after you transformed it, you get it into this direction. So this is an example of a shear operation. So a shear is equivalent to, taking sort of a rigid object, okay, not exactly a rigid object. So for example, I have this paper here. So if you see it, um, so you have this. Oops. Okay. Yeah. So you have this cuboid, as you can see here. Okay. As you can see here. And now what I'm doing is I am pushing the top part like this. Like this. But you notice that the bottom part remains the same. And I'm pushing the top part this way. This is what is called a shear operation. Okay. So I'm not a physics guy, but I think it is a common operations in elasticity and things like that, which is studied in physics. So that is the same thing that is happening here. Okay. So if similarly, if you look at what is called a unit cube, so if you look at points that look like this, and when you apply a shear operation, then it will map the points uh, somewhat like this, somewhat like this. Okay. Oh, thank you, Rohan. Yeah. Okay, I'm glad you like the uh, uh, extempore example. Yeah. Okay. So yeah, Goel, to answer that, you can change the direction using vectors. Okay.
Yes, yes.
Okay. And okay, so that is about linear transformation. I'll just shift this guy to. Okay, I'll shift this guy to there. Okay, and the next thing is the second part is what I call eigenvalues. Okay, eigenvalues and eigenvectors. Okay, now this is a very interesting concept. Okay, and well, in theory, I think we all have studied. Okay, and that for you are given a vector. No, not a vector, a transform, a matrix. Okay, A. Okay. Now the important part of the course is that don't view a matrix just as a matrix. Okay. Of course, I've said several times before that okay, a matrix is a collection of vectors. Okay, but also note that a matrix is also it also represents a linear transformation. Okay, so matrix A, or instead of that, I can also call it a linear transformation A. Okay, because you know that when I multiply a matrix to a vector, then it may change some things about the vector. So what I would say is don't view just matrix as an object. Okay, not just as an object, but see matrix as an operation. Okay, so the this matrix represents an operation. Okay, now so you can always call a matrix a linear transformation. Now I can say, instead of saying given a matrix, I'm going to say given a linear transformation to you. Okay, given a linear transformation, and I'm calling it A. So when I multiply that A, that which is my transformation, to a vector V, it may do arbitrary stuff to me. Right, it may do arbitrary stuff to be, for example, like I showed that shear thing, right? So if it was there, then it, because of the shear, it got shifted here. And what will be the effect for if similarly if this got shifted here, maybe that same transformation, if I apply to this vector, maybe when I apply that same operation A, it got shifted in some, since we are still talking about shear, maybe it became this guy. And maybe this red vector is very long and pointing here. Okay, this red vector, on applying that transformation, got shifted here. So this operation A in that family of vectors, which we are focusing on R3, right? R cube represents all possible vectors over real numbers, three dimensional vectors over real numbers. Okay, and imagine this infinite three-dimensional space, and you're applying this linear transformation, which is nothing but a matrix, okay, on those vectors. Then it may transport these points into arbitrary places, change the direction of the vectors, lengthen the vector or decrease the vector. Now what you want to say is, ask, is it possible that given a linear transformation, I can guarantee that there are vectors, okay, that when I apply the linear transformation, just there are vectors that when I apply the linear transformation still remains in the same direction. The direction is unchanged. That is the question. And these vectors always exist, and these are what are called eigenvectors. Okay, of course, it may lengthen the vector or decrease the size of the vector, shrink the vector, what is called shrink. Okay, either lengthen or shrink the vector. The factor by which this lengthening or shrinking happens in the same direction is what is called the eigenvalue. Okay, so if this was the vector v, this guy in the same direction became kv, where k is a scalar. And what is k? Here v is an eigenvector for a, that operation, linear combination, or equivalently, like I said, a is also a matrix. Okay, and here k, what is k? K is what is called your eigenvalue. Okay, there are limited amount of eigenvalues for a particular dimension, but remember, eigenvalues could be infinite. Eigenvectors could be infinite. Okay, we'll soon see that concept, why it could be infinite. Okay, but that is the geometric interpretation. And so does there exist an a with a v? Okay, so given a, you're already given a, fixed a. Does there exist a vector which, when operated on, which means multiplied by the matrix A, gives lambda v, where lambda is a scalar? That is the question. And what does this mean? This means and here lambda is what is called an eigenvalue, and v is a eigenvector corresponding to it. Okay, I hope that is clear. Now, always note that if v is the zero vector, okay, then AV equals lambda v is always true. I just put 0 out here. A scalar multiplied with 0 vector is 0, and any matrix multiplied with 0 vector is 0. So I will insist that v needs to be non-zero. Okay, because this is v being 0 is always a trivial solution. Oops. Okay. Therefore, v is taken to be non-zero. But geometrically, what does it mean? If I have a zero vector, which means length is 0, direction is 0. Okay, I cannot apply a multiplication operation. I cannot apply any kind of linear operation that is going to shift this guy. That is going to. I cannot. It will always be that whatever linear transformation I do, 0 will always be mapped to 0. Okay, so in other sense, I cannot sort of shift this guy. Okay. Okay, so that is done with. Now let's move on to the main questions. Okay, so this is a rather simple question. This first one is a rather simple question. I just want you guys to look at it. Okay, let v be an arbitrary vector over R cube. Is it true that for any linear transformation, st over r cube. Now remember, when I say linear transformation, st means matrices. Okay. Is it true that if I apply the transformation t over on the vector v and then I apply the transformation s on that, it is same as t applying s first and then t? Okay,
So matrix multiplication are not commutative. So this what we do.
yeah, that is the simple answer. So this was a very simple question. Just want to just put it in your drill this concept in your head that linear transformation and matrix multiplication are the same thing. So yes, it is not true, or rather, no, it is not true. Yeah, but we can look for when it happens. Meaning, but we can look for when it happens for which t and s they'll commute. Is there a ready-made answer? Okay, that is a good question. Like, when do two matrices commute? Right. So that is not an easy check to do, as far as I know. Okay. When do two matrices commute? So what you want to say is something like s and t is equal to t times s. Yeah, this question is a very algebraic question. It's asking whether this is an abelian group. Finding an abelian subset.
So if one of the matrix is an identity matrix and the other one could be any matrix, then it won't matter whether you multiply identity matrix with A or
no. But that is one single example. No, can you find a family of, not even family of, can you get a test of whether two matrices st commute? Well, one test would be you actually try it, right? So one test would be you have st, you just multiply s and t and then do t times s and check. But is there a faster way? I think that is what Rohan is asking, right?
Yes, sir. Yeah.
Yeah.
So,
okay. Yeah. So can you characterize the set of all pairs of commutative matrices?
Like say, what about the symmetric matrices? So basically, if we have same row and same column kind of a thing, even if I take the transpose, so if I find the transpose of a matrix is same as the matrix itself, then probably
that is a good idea actually, because transpose sort of represents right multiplication. I mean, shifting from left to right multiplication. That is true. So maybe symmetric matrices characterize it. That is actually a good thought. Yes.
So actually, I think symmetricity has nothing to do with commutativity. It might look like I got your point, and I got his point as well. That he is saying that that AB whole transpose is something like B transpose A transpose. Then we can use those transpose facts to bring that into picture. But I think symmetricity has nothing to do with commutativity. Actually, I was asking this because in a weekly quiz 1 or 2, there was a question like this, that AB equal to BA happens for which matrices. So in one of those assignments, very early one, maybe 1 or 2. So that time I was thinking similar like him, that if one is identity, or let's say if
That's
one
right.
is zero matrix,
That's right.
or if one matrix is A, another is A square, this kind of a thing, polynomials in the same matrices. So in those things that are happening, but I was algebraically so much concentrated. But when we have learned linear transformation, so basically we are moving towards geometry.
Yeah.
Now can we think of something which will help us know that when the commutativity will come into picture, not by looking at the matrix multiplications, but maybe because they have a linear transformation associated with them. So is there something that from linear transformation can we jump into commutativity or this kind of questions? I'm not sure actually. That's why I was asking you.
No. I mean, it's a valid question to ask. So, but I still think the question, the core of your question is still that what are the set of pairs, okay, that commute, right? The pairs of matrices that actually commute. That's the core, right? And identity is still symmetric, and zero matrix is still symmetric. So were you able to find a counter example where the pairs of matrices are symmetric but actually they do not commute?
Yes, lots of, like, you take
Okay.
any matrix
Okay.
and which is not symmetric, and maybe you raise its power to 2 or 3. So let's take a non-symmetric matrix A.
I mean symmetric. So our conjecture is
Oh,
that
okay. So you are
symmetric.
asking.
Yeah.
Okay, I got you. You are asking, is there any symmetric matrix which does not commute?
Exactly. Two symmetric matrices that do not commute.
Okay, I think we can find some. Yeah, let's try.
Sure. Okay. Okay. Let's see. Okay. The simplest would be something like, I don't know, 1, 2, 3, 1, 2, 3, and 2, 1. Okay, not 2, 4, 5, and here should be 5, and this is, say, 1. Is this fine? This is symmetric, right? Yeah.
Yeah.
Okay. No, okay. This is not so simple. Maybe we'll do a simpler one next.
Yeah, we can take a 2 by 2 example, I think.
Yeah, that's better actually. Else we'll be lost in the multiplication.
Right.
So 1, 2, 2, 1. Is that fine? Yeah. Times, okay. Everything will look something like this, right? Uh, s- um, uh, 3, 2, 2, 3. Okay. Right? So now what will this become? 3 plus 4 is 7. 2 plus 6 is 8. 6 plus 2 is 8. 4 plus 3 is 7. Okay. Now let's do the other way around. 1, 2, 2, 1. Okay. Let's see. 3 1s. Okay, it's already not commuting. Oh wait, it is commuting.
Right.
7.
Okay.
3 2 is 6. 6 plus 2 is 8. Yeah, it is commuting, right?
I found one example, sir. Can you write this?
Sure.
So first matrix is 1 0 0 3.
1 0 0 3.
And the second matrix is 0 1 1 0.
0 1 1 0. Okay.
So if we multiply in this order, then it is becoming 0.
Okay, this is 0 1
1 3
3
and 0.
0. Yes. Okay, and
Now
if we flip
multiply
it,
in the reverse order,
then
I
it'll
think it
come
will work because of the zeros.
0 3. Oh, okay. Yeah. Good. And
So the 0
1
0 helped me.
0, right?
Right.
Okay, nice. Yeah. So symmetricity is still not implying commutativity. Okay. That is a good question, actually. I'm thinking in terms of it algebraically only. If what you're looking for is like an abelian semi-group.
So probably the question is that the impact of, say, the product of A and B would be like, say, I create an impact, say X, followed by an impact Y.
That's right.
This is the meaning of the two transformations, say
That's
A
right.
and B.
That's right.
And if I want this to become equals to BA, that would be same as that if I create the impact Y first,
That's right.
and then I create the impact X first,
That's
and
right.
I should be able to reach to the same position. Same thing should happen.
Exactly.
So I move left and then I move right. Would it be same as that I move right and then I move left? Probably that would be same. So
Yeah,
if I have two matrices which are creating, say, this kind of the impact only, say one dimensional impact, probably that the impact of the one matrix is I make a right move by some amount, and the impact of the second matrix is I make a left move by the same amount. So I will remain at the same position. In that case, the AV would be same.
not that you will remain in the same position. You will you need to land in the position that you were previously doing with the operation in the reverse order. That's right.
Yes.
Geometrically, that is the interpretation. How do you characterize
I think
it? That is the question.
yeah, I think he's giving one example of it, like the simplest one, which is very easy to picturize. So he said we are moving 2 steps to the right and then maybe 1 step to the left, and maybe that's after doing this kind of operation, wherever we are landing, we'll reach the same if we do it in the reverse order. So that's a very that's right actually, but it represents only one kind of a thing. There are some other things as well. For those also, AB equal to BA will happen. I think there isn't any ready-made because I haven't encountered any. So we can take this question. Maybe I'll write this question and we can discuss it later.
Yeah, that's what. So so the question is still that you want to characterize, right? You want to look for a characterization. Characterize the set of pairs of matrices that commute. Okay, it's not really a billion because you just want to look for pairs. It need not commute with all of them. Okay, so we'll look for this. Okay, I'll look into this. It's a good question to actually start the session with. So yeah, we'll look for this and then come up with answer in the next session. Okay. Okay. Thank you. Okay. Here is another question. So the question says, let A be this matrix. Okay, be a linear map in R cube. Compute the determinant of A. Okay. Interpret the determinant geometrically in terms of volume scaling and then C part. Okay, we'll look at that later. Okay, let's look at the first. Compute the determinant of A. Okay, so can you say what the determinant of this matrix is?
So there would be 1.
Okay, 1. That's good. Correct. So it's already in this nice staircase form, right? And you can just see that it's just 1 times 1 times 1, which is equal to 1. Okay, and but I can apply the determinant formula also, but and then I'll finally get it 1. But this is like a shortcut trick to actually do this if it is an upper triangular matrix. Okay, now yeah, that's right. For triangular matrices, that this happens. Okay. Now, but what I want to do, what the question asks is interpret the determinant geometrically in terms of volume scaling. So this is a 3-dimensional space, right? Operation. Okay. So what you have is, when I say that A, determinant of A is some value k, what I mean is the resulting volume, okay, of the operation, okay, is scaled by a factor of k. Okay, now, but what do you mean by, resulting volume is scaled by a factor of k? So that is when you compare it. Okay, this is when what is called the unit cube is helpful. Okay, so what you look at is what is called a unit cube. So what does a unit cube look like? If I consider this to be 1, 2, 2, 3, and here 1, 2, 3. Now this is 2 dimensions. Okay, what does a unit square look like? This is a unit square. Not only is it this, it is everything inside. So all vectors in 0, 1, 2, 3. Now observe these square brackets. Okay, these square brackets means all reals between 0 to 1. Okay, so not cube here, here it's square. Okay, so all vectors in this. So this is a unit square. Now what I'm doing is I'm looking at a third axis. Okay, and bring a cube here, and so all the sides are 1 here, and look at all the vectors inside it. Okay, and this now becomes a unit cube. Okay, what is the volume of the unit cube? What is the volume of the unit cube? 1. Correct. Yeah. So it's just all the sides multiplied, right? Because so how much does it contain? Well, if you have a cube which is like 1 meter by 1 meter by 1 meter, then what is the how much water is stored in it fully? It's just 1 meter cubed. Okay, so you do 1 times 1 times 1, which is equal to 1 unit. 1 units. Okay, good. Now okay, now happens the now is the interesting thing. So it means that if I take this unit cube, okay, and then apply the transformation here, the transformation may look very strange. It may not look very neat. It may not necessarily be a shear, let's say. It may not necessarily be a rotation. It may not necessarily be what is that? A translation. Okay. It may be arbitrary. It may look like an arbitrary shape. Okay. But so this is the applying the transformation A on the unit cube, the set of vectors of unit cube. Okay, the set of vectors of unit cube. Right. But the interesting thing is the volume is changed by the determinant of A, by a factor of determinant of A. What is the new volume? The new volume is the determinant of A, the representative of, yeah, I mean, it's okay. I mean, we can use that representation or not. Okay, it's up to our discretion. That's fine. But if you want this, it's fine. The transformation of right.
Sir, actually, I was asking a doubt. So basically, when you are saying something, I'm trying to picturize how the matrix multiplication is happening. So
Right.
for this unit cube, if I'm considering I3, so later on, if you are saying, Rohan, I have a transformation on a volume of a particular cube, which is not a unit cube. So then should I be assuming the three vectors which create that particular cube, and should I be putting them column wise to represent that cube that you are saying? So I want to know what a cube means in a matrix. So
what does a cube mean in a matrix? Just picture all the all the vectors which sit here. So that's what I mean. Something is what my pencil is. Okay, yeah, now it's right. Okay, so what I mean is, see, of course, you can. It is a bit difficult to explain it when I'm talking about the an arbitrary vector. Okay, so that's what I mean. So what I want to say is why because if you remember, right, that if I have a collection of vectors like 1 2 2 1, okay, and it may look like this or like this, and then you look at the parallelogram, okay,
Yes, sir. Yeah.
And you look at the parallelogram, and this represents the determinant. Of course, you can look at this. This represents the determinant, and of course, you can see it this way. Okay, and this is the resultant of these two vectors.
Right.
But now I'm not talking about a collection of vectors. Okay, you can interpret it this way, and by this also you land into the correct answer only, correct interpretation. You can interpret it this way, but I don't want to look at it as a collection of vectors. All I want to look at it as a linear transformation. What does it mean when I compute the determinant of a linear transformation? Because this is also matrix only. No? This was a collection of vectors. This was a matrix. I can compute the determinant. But now what I'm doing is I'm looking at a linear transformation, which is in this case a square matrix. Okay, in this case, which is a square matrix. And what I want to do is I want to see what the determinant means in this case for a linear transformation. I'm not talking about a collection of vectors in this case. Although you can interpret it that way and end up at the correct solution only, because under the covers the same thing is happening. Okay, Rohan.
Okay. Right.
Okay.
Right, sir. Got you. Yeah.
Okay. So now the question is, what does the determinant of a linear transformation denote? So that's why it's always simple to talk in terms of a unit cube. You can take a bigger cube. It's okay. Okay, because it will just scale up accordingly. But now look at the unit cube, and then what I simply mean is look at all the vectors sitting inside this guy. Okay, several arrows inside. Now what you did was it arbitrarily changes the dimension, not the dimension, sorry, it arbitrarily repositions all the vectors to different places. And maybe we can analyze this matrix and then say that, oh, maybe it does a shear or maybe it does a translation, but I'm not interested in that. All I'm saying is, if you do this to a unit cube and then you get some weird, strange object, the volume only changes by a factor of the determinant. So the volume is just volume of A times the volume of the unit cube. Okay. Now, why is this happening? Because, like you were talking, I mean, if you prefer this definition, then it is happening because of this. You can try it offline, okay, and you consider like all the vectors sitting inside and look at their displacement, okay, on taking this matrix. Why I want to take the unit cube? Because when you multiply it with the unit cube, okay, now it's clear, right? When you multiply it with your cube, things become much simpler, okay, when you look into the proof of this. But all I want to say is this fact: it is the size of the determinant times the volume of the unit cube. Okay, the new volume of the original unit cube. And in this case, what is A? It is 1. And volume of the unit cube is, of course, again 1. So the new volume is still 1. So what does it mean geometrically? What does determinant of a linear transformation mean geometrically? Okay. In this case, suppose. So in this case, the determinant is 1, which means when I apply this operation, the volume remains the same. See. So it does not scale anything in this case. That's not right, Ron, because it may scale some vectors, but it will also
no, sir. For volume only, I was saying that.
Oh yeah,
for volume only,
yeah,
it is not scaling.
Exactly, volume it won't scale. Exactly. Yeah. Right. So part C is simple. It just says that B is another linear map with determinant B equals 2. Then compare the volume scale effects. One will double the volume, and one will just keep the volume as C. Okay. Great. So this is just a concept I wanted you guys to see once. Okay. And here is another question. Okay. Let n denote a linear transformation. So you can try this one. Okay. N is a linear transformation, and n square is 0. So that show that z if okay, no, there is no if. Show that 0 is the only eigenvalue of n.
Yes, sir. We can do one thing, I guess. We can use the property of eigenvalues and eigenvector.
Okay.
So nx, let's say x is a vector. So nx would be lambda x.
and x is your vector, right? Okay, is equal to lambda x. This is the definition of linear transformation.
So here lambda is our eigenvalue.
Correct.
We'll just multiply n with both sides.
Good.
That is, we'll take another linear transformation.
So you left multiply.
The left hand
right?
side will become 0. Correct.
Left multiply by n on both sides. Okay. And then what you'll get is n square x equals n lambda x. Okay.
Right. So that says lambda into nx equal to 0. The LHS is 0 because n square is 0. They have given n square is 0, right?
So yeah. So n square x. I can take this lambda to the left, right? First.
Right. Yeah.
Okay. And
then n square is 0.
N square is 0. Yeah. This guy is 0.
Lambda into nx is 0.
So yeah. One moment. 0 times this equals. I'm just listing out so that it's simple.
Yeah. Sure, sir. Sure,
okay.
sir.
Yeah. Okay. Now, what does this mean? Right. So this means that lambda times n should be 0, right? Because this is a null vector. This is not just a null. This is not just a scalar 0. Okay. So no matter what you multiply x with, it's going to bring it to 0. It's going to bring the product to a null vector to 0. So this can only happen when this guy itself is a null vector. So you have lambda times n, right? And n is not necessarily a 0 vector. This is not necessarily true when n is 0. So this means that lambda always has.
Or else we can make one more simplification, like say nx is equal to lambda x. So if we put that value in the right hand side, it will become lambda square and then x. So then no other need to no other thing need to be considered.
Yeah. Good. Yeah, that's another way to do it. So what you mean is, since nx is lambda x, you can write it as lambda square x, right? N square x is equal to lambda square x, and you have that this is 0 times x, which is equal to lambda square x. Good. Yeah. So from here you get that lambda square is 0. So lambda is also 0. Okay.
Yes, sir. So actually, now, this is one more condition should be given in the question. I think that n not equal to 0, because if they do not give that condition, then I think whatever they're asking, show that 0 is the only eigenvalue of n, is not true. So they must give that n not equal to 0 in the question.
No, that's oh, okay. So what you mean is that if n is 0, then lambda can be arbitrary and still yeah. That's correct. That's correct. For this question, that is right. So n is not equal to 0 vector. But why I gave this is because I had split it into 2 parts. Okay, and therefore this not equal to 0 becomes an important catch. Yeah, good catch. Okay, and but why is this interesting? Because like it holds in the other direction also. The converse is also true. Okay, but this I want you guys to try it. Okay, but it won't be as straightforward as the previous one. Okay, because here you are working with this vector multiplication, things become simpler. Here it's not so straightforward, but try it, and this will say that this is an if and only if. Basically, it's not just that if b square is 0, then the only eigenvalue is 0. It's also holds the opposite direction, that the only eigenvalue is 0, then b square is 0 vector. Okay, so this characterizes having just 0 as the eigenvector. Additionally, I just want to ask you, what does it mean to have the only eigenvalue as 0 vector?
So the meaning could be like this, that let's say A is a matrix which has 0 as the only eigenvalue. That means all the eigenvectors that A might have, they will do one thing: Ax equal to 0x. So there is no So the thing is, there is no vector in that plane. Let's say R3 or Rn. There is no vector after on which if you apply that matrix transformation, it will scale or it will scale or shrink it can only go back to 0. So something like it will go back to 0, but nothing else will happen for any other vector. Am I right?
Yeah, I mean, somewhat. I mean, yeah, you can say that you are right. It just means that you will you will the only thing that the matrix is able to do is, you know, what is called a crush those vectors and make it to dimension 0. So it's like a destroying operation. So the only way that it's able to preserve a direction of a vector is by crushing the entire the entire magnitude of the vector, and that's the only so that's the way how you can interpret it.
Sure. And as you said, it will crush. So it will crush a very particular set of vectors, right? Those eigenvectors.
That's right. That's right.
It will not crush any vector, right?
It's not true that it will crush any vector, because otherwise, if it crushed every vector, then yeah, that's a good question. What will happen if it is crushing every vector to 0?
Then I think the matrix has to be 0 only.
Exactly, the matrix has to be 0. So it's not true that it will crush all the vectors. It will crush only a specific amount of vectors, which are called eigenvectors, right? The only way that it's going to preserve the direction of these set of vectors is by crushing these vectors to 0.
Okay, so can you rephrase it a little bit and give a simpler version meaning of eigenvectors? That is, the crushing example is very nice to my ears.
Yeah.
So it is crushing some vectors to 0. Now, what vectors it is crushing to 0? Can you say? Not saying eigenvector, but yeah.
No, it's so that could be. So it depends on how the matrices are displaced, right? So what, like the previous example that I was giving, that it shifts this guy to here, and it shifts this guy to here. Now what I'm saying is, if it so happens that it shifts this guy to here, okay, in the same direction, the blue vector in the same direction, then this is a special case, and this is what is called an eigenvector. The original guy is what is called an eigenvector, and the amount of scaling that happens is k. Right?
Right.
Now, if it so happens that n is non-zero, okay, first of all, because if n is 0, then it will crush everything.
Right.
So then all these eigenvectors, there could be several or there could be infinite, okay, eigenvectors. So let's say this is an eigenvector. The only way that it's able to preserve the direction is by collapsing it and bringing it back to the origin.
Okay, nice. Yeah.
Okay. So
yes.
So and b square. What am I saying? Okay, yeah. This is also an example of what is called a nilpotent matrix. So that's when on powering you are finally going to get a 0. Okay.
So Sandy, what is the name that you said? What kind of a matrix?
Nilpotent. You can look into that.
Nilpotent. Okay, right.
Yeah.
Nilpotent. Yeah.
Okay.
Yeah.
So okay. So that is another way of looking at it geometrically. Okay. Let's move on. So okay, I need to paste the question. Okay. So please look at try the converse direction. Okay. But I'm going to move.
So sorry for interrupting. Just one question. Sir, actually, earlier I didn't attempted this video lectures kind of thing taken by you. So from now on, I will.
Yeah.
So whatever you're giving as a try this. So if you're facing any problem, can we discuss it in the later class?
Yeah, we can. Actually, I will discuss on the next class. Don't worry. Okay.
Okay. Cool.
Okay. Yeah. Yeah, Mr. Shivkumar, you have raised your hand. Yes. Do you have any question?
This
Yeah.
eigenvalue 0 means lambda is 0. Am I
Right. Lambda is 0.
Yeah, that question was in this lambda is 0. Okay,
Right.
Thanks.
Yeah. So lambda is 0. Yeah, sorry, I am using this notation k over and over again. I just used k in the beginning and I kept using it. This should be lambda. in a standard form, in a standard writing. Okay, so yeah, eigenvalue is 0 means lambda is 0, and if lambda is 0, it means that that vector is brought to the origin. So that's what I meant by the crushing operation. Okay, okay, okay. So here's the question: given the matrix M, find the eigenvalues of M. Okay, so try this question, or just let me know if you want me to try it. So, well, if you don't know the technique, then you need to find what is called the characteristic vector.
So is there something relation in between the eigenvalues and the trace of a matrix? The sum of
Yeah.
entries
The sum of the eigenvalues will be equal to the trace, right? Yeah, that is true. You can prove it. How will you prove it? Okay, I don't have a quick proof in mind right now. Maybe it'll take some time to come up with it. But that's right. Well, so it's related to the trace. It's related to the determinant. For example, the product of the eigenvalues.
Oh yes.
And okay, I can't help but bring complexity into it. But since you have a complexity background, I would like you to look at expanders. Okay, eigenvalues have huge application. Expander graphs.
Yes.
Okay. You should check this out. Okay. Oh yeah, good one. Yeah, that's. I think that is the answer. Yeah, let's check. Or would you like some more time?
Sir, I have one question. So,
Sorry.
for this kind of matrices, again, it is a triangular. So, finding the characteristic equation for this particular matrix is very easy because you'll apply the same determinant is simply that product of those diagonal matrices. But let's say if it is not a triangular matrix and you're asking me the same question, what will be your take on this? Will you go by the determinant and trace method? Like the product of the eigenvalues, sum of the eigenvalues, or you
that's I mean that is sort of the shortcut way to do it. If your if this is 3-dimensional, right? If your matrix is 3-dimensional, if it's like a higher dimensional matrix, then I don't know there's a neat way to actually characterize it in terms of trace and product of product of diagonals and so on. So what is the chief formula? I mean, the master formula is still that the determinant of a minus lambda I is equal to 0, right? So this is what you are using. But it so happens for a 3-dimensional matrix, you can represent the coefficients as trace or something else, right? So this is the preferred way to do it.
Okay, sir.
Okay. But if you try to prove it by using A, B, C, D, E, F, then you'll see that the coefficients are nothing but trace and product. Okay. Okay. So yeah.
Yes, sir.
But how did we get this? Well, we were saying that A V is this is called M. This matrix is M. MV equals lambda V, and then we shift this here. Okay, I'm not going to go into the details, but still it's something like M minus lambda I times V is 0. So if for this to happen, the determinant of M minus lambda I is equal to 0, and therefore I use this formula. Okay. So what do I get? Determinant of M minus lambda I. So that will, since I is a I looks like 1 0 0 0 1 0 0 0 1, and I multiply that I with lambda here. So only the diagonal entries are multiplied with lambda, which means when I'm doing M minus lambda I, I'm subtracting the lambda from each of the diagonal elements. Okay, so which means what is M originally? 4 minus lambda 1 0 0 4 minus lambda 1 0 0 4 minus lambda. Oh, okay. I additionally, I think Rohan, that question about that trace and stuff, right? you were asking what if this is not
Yes.
diagonal, then you can always use row operations and column operations in this case. So to simplify the if it is not a diagonal matrix.
Okay, right. That's a good idea. Yeah.
Okay. But in this case, this is diagonal. Okay, again, good for us. It just means it's a product of the diagonal elements, like we saw earlier, and this is supposed to be 0. So what does it mean? It means that 4 minus lambda is equal to 0, which means that lambda equals 4. But there are 3
Repeated roots.
Yeah, repeated roots. Okay. So lambda is 4, 4, 4. Good.
So doing a row operation won't help, I guess, because lambda is there, no? So how will you choose a coefficient multiplying with the first row that will vanish the below entry? Let's say 0 is not there. Let's say 5 is there. 4 minus lambda, and below it is 5 there. So what kind of row operation will you perform to vanish 5?
Let's see. That's a good question. If I apply a row operation, I can always do this. No, I can.
You can do this actually, but
multiply,
will it be something simple, or like that will be okay? Sorry. So, tell me your way. I think
you will you'll multiply this guy by 5 and subtract it from this column, right? And then you will get an additional factor of lambda, some 5 times 4 minus lambda, and then you'll subtract from here, and that would be the idea.
Okay. We can actually. So theoretically we can. I think calculating it will be little bit time taking. Yeah.
Yeah, it could be time consuming, and sometimes it could be like so tedious.
Easier also.
Yeah.
Okay. Thank you.
Okay, good. So so the eigenvalues are 4, 4, 4. Now for each of the eigenvalue, compute the corresponding eigenvectors. Okay, how do you do this? So you are saying compute the eigenvectors corresponding to these guys. So what you have is, now you have m times a vector equals lambda times a vector, and m right? It's 410541004. 410541004. Okay, and this you are multiplying with a vector which you don't know. Let me call it v1, v2, v3. Okay, and now what you are doing is you're substituting lambda. You're doing 4 times v1, v2, v3. Okay, and so what you get is 4. Okay, now we can write it as a system of linear equations, right? 4v1 plus v2 plus 0 equals 4v1. Okay, so I'm multiplying it here, and 5v1 plus 4v2 plus v3 equals 4v2, and one moment. Oops.
So the 5 will not come there. 5v1 will not come there.
5v1 will not come there. But why is that the case? This 5 is multiplied with
0,
this. No? What is 0?
0 is there, no? In m21 is 0, no?
Oh, sorry. Yeah. Okay. Is there a 0 there? Oh God. Okay. Sorry. I was looking. Thank you. Okay. I don't know how I saw a 5 there. Okay. 0, and this is v1 will not be there. Okay, good. And here just 4v3 is equal to v3. Now we can just apply a simple substitution, okay, to do this. 4v3 is equal to v3. Is that correct? 4v3. Okay, so yeah, this is an interesting thing. Okay, Now what you get is 4v3 is equal to 4v3. So you're going to think that you can't really solve the system, right? Yeah, there's a message here. Rohan is saying eigenvectors is 0, 0, 1.
Sorry, sir. That was a mistake. So I think it will be 1, 0, 0.
Okay. C times 1, 0, 0. So a scalar times 1, 0, 0.
Yeah, right.
Okay. Good. Okay. So let's see. Okay. So let's see. Okay. So what does this mean? So 4v3 equals 4v3. So v3 equals v3. Okay, great. v3 equals v3. Now, but we have these two equations left. No, let's use them. Okay. So 4v1 plus v2 equals 4v1. Okay. So what do you have? We have v2 is equal to 0. Right. And here what do you have? 4v2 and v2 is cancelled. So v3 equals 0. And v3 equals v3. Nothing is wrong with this. Let's just write what we know. Okay, let's just write what we know. Eigenvector equals 0, 0, v3. Because v3 equals
Sir,
yeah.
v1, 0, 0.
Okay.
The same mistake I did actually.
v1, 0, 0. Why? Okay, why was this mistake here then?
So you calculated v2 and v3 as 0, right? So v1 we don't know anything about.
Okay.
So
v3 is okay. So good. Okay. So v3 is equal to v3. So this is this, but we still calculate v3 equals 0. That's correct. Yeah. Now, what about v1? That's the question we want to ask. Okay. What about v1? We don't know what v1 is, and that's perfectly fine. Okay. v1, v2 is 0, and v3 is 0. We know that. But what does this represent? Okay, what do you mean by v1, 0, 0? So this is fixed, and this is what is called a free variable, okay, or a variable. So this can be anything. So this not just represent one vector; it represents a family of vectors. Okay, so v1 can be anything from reals, 1, 2, 3, 3.5, whatever. It does not matter. So what does this mean? So this is your first example, okay, of what I was talking about, that eigenvalues are limited, but eigenvectors are unlimited. Okay, I mean, it may be unlimited, not always the case, but this is an example. And so you have infinitely many eigenvectors which are of this kind. Okay, so what does this mean? So if I plot it, and I'll just look at the simplest case, okay, that is when v1 is equal to 1, then it becomes a 1, 0, 0. So in x it is a 1. So in x it is a 1. Okay, so this is an x-axis, this is the y-axis, and this is the z-axis. Okay, in x it is a 1. And what about y and z? It's a 0. So it does not have depth, it does not have height. So this is what the vector looks like. Okay, this is what the vector looks like. So what does it mean? What does it mean? When I apply matrix M, okay, so this is the third question. Discuss the geometric interpretation. Okay. When I apply this matrix M to these vectors, it may get changed, okay, or let me represent it by dotted lines. So it may get changed like this, okay, may get changed to even, let's say, in an opposite direction, okay, and shortened, lengthened, whatever. But if the vector is of the form v1, 0, 0, which means it could be 2, 0, 0 or 3, 0, 0. Okay, let's just look at the case of v1, 0, 0 for now, 1, 0, 0 for now. for example, this guy is 1, 0, 0. This gets transformed when you apply M, when you apply matrix M times lambda equals, what is it? Sorry, not lambda, M times V, okay, equals lambda, which is for us K at this point, 1, 0, 0. So it becomes 4, 0, 0. What is 4, 0, 0? It's just, let's say, 1, 2, 3. This is 4, right? So this is 4, 0, 0. So it gets transformed. The direction is preserved, okay, and but the size of the vector is increased by a factor of 4. Okay, yeah, or it stretches anything on this axis by 4 times, because if you take, say, something like if you take, okay, let me take another color, purple. Okay, if that purple guy is here, okay, and this is 2, 0, 0, 2 4s are 8, so somewhere around here, 8, 0, 0, anywhere on this axis, okay, this is stretched by 4 times, and all the other guys are not stretched in the same direction. They can go in arbitrary direction, except that except the direction that they are already on. Okay.
I have a query here. So
Yeah.
how do we define this M square thing? Say M is a matrix, then how do we define M square? Will this be the product of M with itself or something else?
Okay. How do you define M square?
M square, yes.
How do you define M square? Well, you do the operation once and you do the operation once again. Right. It's like if R is a rotation matrix and R prime is a reflection matrix, you first rotate and then you reflect, right? But what does R square mean? You rotate 2 times.
Oh, I see.
Right. Similarly, you just you are applying M and doing some operation and then applying M once again.
Oh, I see. So does this mean that if M has an eigenvalue lambda, then M square would be having one of
lambda square? That's right. That's right. That's why this is happening. Yeah.
Oh, okay. So all right. So M raised to the power n x would be having, say, lambda raised to the power n is one of
right.
its
Good. Yeah, that's right. That's right. Is there a factor? There could be a dimensional factor also. It could depend on the dimension of the matrix. I'm not totally sure it's just square. It could be. There should be a dimensional factor also, but you get the idea, right? Yeah.
Oh, I see. So there could be a situation then wherein the M raised to the power n plus n and then x is same as, say, mx, or because if I keep on multiplying, say, m and then m square and then say m raised to the power n, and this transformation, and if I apply this m transformation one more time, then quite possible that we may come back to the original value, and it will so happen that m raised to the power n plus 1 x is equal to mx. What would
it can happen actually. So he's looking for, I think, periodic matrices or something like that, which in turn of multiplying itself will bring back to identity. I think you're looking for something like this, are you?
I mean that.
Yes, that sort of the thing wherein I keep on multiplying, keep on carrying out the transformation, and one more transformation will give me everything back.
See, that's possible for. I mean, if you are looking for an arbitrary vector, that can always be possible. For example, a rotation vector. If you rotate by 90, 90, 90, 90, then you get back 180. 360. It happens, but for eigenvectors, I'm not sure whether that happens for eigenvectors. Yeah, it happens for eigenvectors also. Rotation is an example again.
May I give one point?
Yeah.
So there actually exists a matrix called periodic matrix. So whatever Goel is saying, that he will multiply it k times. So maybe some let's say m to the power k plus 1 will bring back m again.
Yeah.
So it happens actually, and that particular class of matrices, they are called periodic matrices.
Oh, okay.
And for which m to the power k will be I.
Interesting. So there, it's okay. That I'm curious whether Okay, since you are calling it periodic matrix and not period of the matrix, it means that there could be aperiodic matrices also,
Uh,
right?
okay, might be. So actually, I know the only class of it, but aperiodic matrices, I'm not very familiar with the
Yeah,
definition
yeah.
or the properties of it.
No, no. I was just asking, does every matrix have a defined period, or is if
No, no,
you
no,
get
no,
it
no.
right? That does not
Only a
happen
few classes
because
of it.
yeah, yeah, because they chose to call it a periodic matrix and not
Right, right, right.
say you
Yeah,
know
yeah, yeah. Right.
alpha
So all
is a
matrices
period of
are
matrix.
not right, right. Only periodic matrices have a defined period which you are looking for, I think,
That's right. That's
and
right. Yeah, yeah.
particularly involuntary matrix for which p square equal to I or m square equal to I will happen. So
Mm-hmm.
that's a very small set of that periodic matrix. But yeah, whatever Goyer is looking for, there exists a class of matrices which are called periodic matrices for which m to the power k plus one happens to be m again. So in the
Yeah.
transformation, exact thing he is looking for. Yeah.
Mm-hmm. Okay. Thanks.
Yeah.
Um, okay. Yeah. Let's continue. Okay. I need to take a screenshot once again. Sorry. Okay. So let's look at this question. We have two final questions. Okay. So, okay, good. Okay, you mean okay, okay, yeah. So, this is a given matrix. The question is saying what is the effect of A on the unit cube? Okay, what is the effect of A on the unit cube in our cube? And so, what do you have here is is 2 0 0 0 1 0 0 0. Okay. Now the question is a bit, yeah, it could, the actual question is what has the effect on volume? But we saw this question already once. Okay. So how do you look at the change in volume by a transformation A? You look at the determinant of A, and in this case also it's a diagonal. Okay. So you just do 2 times 1 into a half, and then you get 1. So the volume remains unchanged. Okay. Okay. And okay, and compute the determinant of A and interpret it geometrically. Okay. So well, it's still the same thing. Now, this is an interesting question. Okay, which directions are stretched and which are compressed by the transformation? Okay, and do you have some ideas on how to think of it?
Uh, yeah. So may I or someone else wanna try?
Yeah,
Yeah.
yeah, Kishore.
What I think is probably the x-axis would be extended, and then the x-y-z, if you take z-axis, will be compressed. Then y-axis remains same.
Okay, okay. Can you give an explanation?
I can give a vague explanation, not fully.
Right.
So comparing the diagonal, right? So one is the standard we can take, and then more than one will be extended, less than one will be compressed.
Yeah, right. And so yeah, good. So I mean, the answer is still simple. Okay, it's like you said, you just take an arbitrary ABC. Okay, and oh yeah, sorry for that, Rohan. Yeah,
Yes, sir. Sorry.
yeah. You also had an idea, right?
Yeah, the same thing, I guess.
Oh,
So
right.
actually, the idea came from the picture that you showed now with that paper example, paper cube.
Oh, yeah.
So
Yes.
I was about to say that you're compressing it from both sides. So the height is getting twice, and the sides are shrinking to half amount. So the volume is keeping the same
Huh.
while the transformation. So I thought of the example that you were showing with a
Yeah.
paper.
Okay. Okay. Good. So I think therefore it makes sense that it's the abstract way of looking at that piece of paper is by looking at the unit cube in some
Right.
sense. Right. Yeah,
At the
Kishore.
object volume will remain same. At the object value will remain same, but the
Volume will
object gets skews.
exactly. The object is in fact in this case is it skewed? Even? Yeah, it is skewed because B is staying same. That's right. That's right. Okay. So so what happens here? This is equal to 2a b and c by 2. Right. 2a b and c by 2. Now let's look at it geometrically. Okay. And here it helps to think of the unit cube. Okay. And you have your unit cube here sitting snugly, and okay. So geometric interpretation is the following. Okay, this is 1. This is say 2, 3, 4. This is 1, 2, 3. This is maybe I should have drawn in front. Okay, but either way, 1. So this is 2. This is 3, 4. Okay. Now, if you have a unit cube, so you multiply the so let's just consider the dimensions, say 1, 1, 1. Okay. So what happens is the x part is multiplied by 2. So this is like the new spot where it goes. Okay. The b part, the v, which is y part, remains same. Okay. So this is y. Okay. So the height remains same. No change. And c by 2, which is the z-axis part, the depth, that changes. That is half. So here. Okay. So now and the transformation is linear, so it's same for everyone, and so this is sort of what the new cube looks like. Observe that the this part is made shorter and this part is made longer, hence the volume is same. Okay, because we computed the volume and the volume is unchanged, the volume remains same because of this, and this is sort of what happens to the unit cube, and therefore you can also translate to what happens to a larger cube or larger set of vectors. Okay, this is the geometric operation version of C. Yes.
That means the new volume is a rectangular cube.
Right. It's a yeah. The new volume is a cuboid. It's a rectangular kind of cube, and if the original dimensions were 1, 1, 1, the new dimensions are 2, 1 and half. Right. The original dimensions were 1, 1, 1. New dimensions 2, 1 half, and the volume is still length into breadth into height, and it's still 1. Right. Okay.
Yes, sir.
Oh, okay. Good. Thanks. Okay. So, okay. Today's session went pretty quickly. So we look at the final question. Okay, maybe the final question will take more time. That's true. Okay. So, yeah, this may take slightly more time. But this is a good question. Okay. So the question says, let T be a linear transformation. Okay. Three-dimensional linear transformation that reflects any vector across the plane x, y, z equals 0. Find the matrix representation of the transformation T with respect to the standard basis. Okay. And okay, don't look at this part. Okay. Otherwise it will spoil the answer. Okay, great. Okay, good. So the question is saying this is the transformation, and I don't want to derive formulas this time because I did it in the last session, and you may already have seen in the recent session in the lectures also. Okay, so I won't do like the formula for a reflection of a matrix and so on. I'll implicitly assume it, but here we have this, and yeah, just one moment, Ron. I'll just explain the problem. Okay. So and what does the plane look like? Well, first of all, of course, it needs to pass something like this for x and y, and for z it should sort of go upwards. So the plane will look something like this maybe. Okay. Now what you want to do is you want to say that I have a vector v, and it needs to be reflected across this plane. Okay, not across x-axis, across this plane, like this. Okay, and let's say there's another vector here, which is v prime, and okay, I have no doubt that you guys can do this because I've done a similar problem before. And but the difference was I was giving you a particular vector. I want you to find the transformation itself that does this. Okay, that reflects, given any vector v, I just multiply with a transformation, let's call it t, and then it achieves the reflection across this plane. Okay, so that's what I want to do. Okay, now that I've explained the problem, okay, yeah, Rohan, you wanted to give an attempt?
Yes, sir. Sure. So basically, I was thinking three-dimensional visualization is not very easy for me. So I was trying to solve a smaller version of that problem. So I was thinking, what if someone asks me that they are asking for a reflection about x plus y equal to 0. So I have reduced the problem from three-dimensional to two-dimensional by eliminating the z-axis. So now my target is to see how reflection about x plus y equal to 0 line looks like. So I'm just drawing two axes. Sir, can you do that with me?
Yeah.
So I have x and y axis.
One moment.
Yeah. And now I'm trying to looking for a reflection about not this line exactly, but the opposite, because x plus y equal to 0.
Plus y equals 0 means x equals minus y, right?
Right.
So
for plane also, it will be slanted in the other way. Like
it
will have
this side. Yeah. So I sort of I should be doing.
Okay, cool, sir. No worry. The idea is same.
Yeah. So the plane should be slanted this way. That's right. Okay. Yeah. We'll just assume that this is the actual plane.
Okay, cool. Okay. Because already the picture looks good, and now revolving, it will be hard.
Yeah.
So now instead of so we have x and y axes, and now we have drawn x plus y equal to 0 line, and now the question asks what will be a reflection of a point about this straight line. So instead of taking any point, we'll take the simplest one. The simplest ones are which lies on x-axis or y-axis. So x-axis, let's take 1, 0, and in y-axis, let's take 0, 1. So we'll try to see what happens to these particular points after reflection. So can we draw 1, 0 on this graph?
Sure.
1, 0. Yeah.
So 1. Let's take this as 1, and this will be 1, 0. Right.
Right.
Okay.
So now if you try to look closer and look clearly, so 1, 0's reflection will be 0, minus 1, right?
So 0, minus 1 will look like 0
This is
here
reflection.
and minus 1 here. Okay.
All right. So as if it's a mirror, and we are looking. Yeah. So am I right on this?
Yeah, you are correct. I don't doubt that. Yeah. So yeah.
Yeah. So it is 0. So 1, 0. Its reflection about that line is 0, minus 1. Similarly, what happens to 0, 1? Let's plot 0, 1. So 0, 1 is yeah.
Yeah. 0, 0, 1. 0,
Yeah, 0,
1 you are seeing. So 0 here and 1 here. Okay. This is 0,
Right.
1.
And similarly, again, if you look closer, can we see the reflection is minus 1, 0?
That's right. That's right.
Yeah. So now the next step I will be doing is, so for my own sake, I'll write 1, 0 and an arrow to minus 1, 0. So these 2 points are going where?
Right.
So
Right.
the thing that is going in my head is, I have a matrix A. Can you write a matrix capital A into a 2 by 2 matrix? In the first column, I have 1, 0, 1, 0 in the first column. And in the second column, I have 0, 1. And equal to. So the thing we got. So 1, 0 got mapped to 0, minus 1. So 0, minus 1 in the first column. 0, minus 1. Right. And in the next column, minus 1, 0.
Right.
Right. So even if we don't solve it particularly, and we try to figure out what A is, I think we can.
You can. I mean, you can substitute A to be say A11, A12, A21, A22, right? And you will see that this is A11 plus A12, right? And this guy is A12, and this guy is A21, and this guy is okay.
So,
wait,
A12
so,
won't be there, no? Or am I wrong? A12 will
yeah,
be
one
multiplied with
piece
0.
is one piece is
A11.
which part? Okay, so this guy. Oh,
The
yeah,
first
A12 won't be here. Yeah, correct.
Right. Yeah.
So this is equal to 0 minus 1 minus 1. That's correct. Yeah.
Yeah. So we got the particular matrix, and it will be our guiding example for what happens in 3D.
That's right.
For
That's
3D, we'll think similarly.
That's right. So this is a problem that we were looking at 2 or maybe 3 weeks ago, and there.
Oh, sorry, sir. Actually, I didn't
No, it's
attend
okay.
the
Yeah,
class.
you were not there that time. I'm not trying to condescend you or something. It's very nice that you actually came up with this. Okay, and there we were doing with this x equals y. Okay,
Oh, okay.
and
Okay.
the similar logic.
Okay.
Okay,
Right.
and this will work. This will work with the plane also. Good. But I want to add one more point. Okay, now I slightly change the field. Okay, I add
Okay.
2x plus 3y.
Okay.
Now things will
So the
become a bit-
visualization is very different, right?
yeah, right. Now it becomes a bit. I understand that it's here, x plus y plus z equals 0, so you can bring it up to a higher dimension. This
Right.
because here there is a empirical observation that 1 0 gets mapped to 0 1 and so on.
Yeah.
Yeah. So that that extra component is there. So that's I would suggest you to look at I won't, because we don't have too much time. I won't explain what how to do for an arbitrary line. Okay, but and the week following that we did it for the line, and then the week following that we did it for a plane. Okay, and but we have this line like you said. Okay, but I'll give you the general idea. Okay, and leave at it. That's fine, right?
Yeah.
Okay, of this technique, that if you have a vector here and let's say this guy, and it gets mapped to, okay, say here, is that correct? Okay, it does not matter. Okay, now
Is it like the midpoint lies on that line, and then putting on the lines equation, you will find some formula? So is it the midpoint thing you will be using?
that's correct. There are two ways to look at it. One midpoint way is one way to look at it. The other way to look at it is in terms of orthogonality.
Okay.
So what is the other way to look at it? Instead of looking at midpoint way, you can always look at it as the midpoint will exactly correspond to a 90-degree angle with the given the source point. Okay, so what you are looking at is a vector. So okay, I'll point this. Okay, so here you are looking at a vector orthogonal to the line, given line. Okay,
Right.
and but it can't be an arbitrary vector orthogonal to the line. No. So what is that called? That's what we call an orthogonal projection. Okay, and
Yes, sir.
once you have this orthogonal projection here, you just want to move by this distance here. But how do you do that? Well, you actually move from here, and if the original is v, then you want to move another factor of v. That's why you get this formula that v minus 2 times projection, orthogonal projection, over the normal to the plane, to the, in this case, a line, and this is the transformation. Okay,
Nice.
so this is another way to look at the I mean, the little advantage of this approach is that you can give me an arbitrary line and this technique still works.
Yeah, true.
Okay, but the question is still, like, from a given line, okay, how do I get a vector? Because I need to work with vectors, no, not lines. Because why do I need a vector? Why is a line not enough? Because I want to calculate this vector orthogonal to this guy, which I'm calling as n. Okay, so this because this formula only the projection is only defined over vectors, not over lines. So you can do a simple thing. You can just say that, oh, you know, this vector is simply x equals minus y. So substituting x equals 1, then what is y? Y is equal to minus 1. So I can always have 1 comma minus 1 representing the vector which represents this line, because it's parallel to it. This vector is enough to represent this line. Okay, is that fine, bro? Yeah, good. So then you can do these operations on it and then get a normal vector to it and so on. That's the hairy business I won't get into now. But if you have a line given as x plus y plus z equals 0, right? Because it needs to pass through the origin. Yeah, 0. X plus y plus z equals 0. How do you get a line corresponding? How do you get a vector corresponding to it? How do you get a vector corresponding to it? So you, in this case, it will look like, so if this is your plane, okay, visually what will it look like? So this it needs to pass through the origin. No? Okay, so if this is your plane, and so you want vectors of this form, which fall exactly on the plane, which lie on the plane, to represent the plane, right?
Yes, sir. Yeah.
right, to represent that plane in terms of vectors. So we did it last week. Okay, I would just ask you to check out those parts of the content, and all you can do is actually look at the lectures to check this. Not the lectures, sorry, the problem solving recordings, and you just take the coefficients, and that is enough. That is enough. So if this was like 2x plus 3y plus z, then 2, 3, 1 is enough to represent all the vectors on the plane. Okay. Similarly, in this case, you have x plus y plus z equals 0. Then 1, 1, 1 is a vector. Okay. Vector corresponding to the plane. Good. Now you've got this guy. Sorry, not the vector, the normal to the vector. Sorry, I made a mistake. So you want these guys, normals, because you want to find the orthogonal projection, no? So these guys. Okay, this is normal. Okay, so now okay, I think now it's a recap for everyone else also. Okay, so therefore I can just directly use this to my advantage. Okay, I can just apply this formula 2 times projection of n v. Okay, and but what is projection of n v? It is dot product of v and n divided by norm, okay, and times norm square. What am I writing? Norm square times the vector itself. So this is the orthogonal formula of orthogonal projection from the vector into this normal to the plane. Okay, and well, what do I get after this? I get let's write it out. V minus 2 times projection is the dot product of the normal, which is dot product of v, which is just v. Okay, just v, and I'll just write it n for now. Okay, divided by norm of 1, 1, 1. What is norm of 1, 1, 1? Root over 1 square plus 1 square plus 1 square, right? Cube root in this case, because it's a 3-dimensional. And what will I get? It will be 1 cube plus 1 cube plus 1 cube whole cube root of that whole cube times normal n, which is 1, 1, 1, which will be v minus 2 times inner product of v and n divided by cube root of cube of cube root, which is nothing, and 1 plus 1 plus 1, which is 3. Okay, and then I get this, and then I get this. Okay, good. So yeah, now the expression seems a bit complicated. Okay, but the nice thing about this is that I have not fixed a vector yet, unlike the previous lecture where there is a fixed vector. Now this equation is very general. Okay, now all I need to do, now this is the part where I think others are others are stuck at compared to the previous lecture, because now you want to find the transformation, you want to find the matrix that does it. So the question is, how do you find the matrix that does it? So the trick is, okay, now the trick is, what you do is you look at the standard basis. Now what do you mean by standard basis? If you check out the lectures, it just means that it is I'm not going to define standard spaces too much because we are yet to enter vector spaces and so on. But if you looked at the lectures, you must have seen that standard basis just represents your axis. Okay, this represents the x-axis, this represents your y-axis, and this represents your z-axis. Now what do? You take this as your v. You take this as your v, and then get 3 column vectors. Club those column vectors together, you'll get a matrix, and that matrix is your transformation matrix. Okay, but why that happens, we'll come to that. Okay, just say V, your matrix V is equal to E1, okay, which is equal to 1, 0, 0. Just substitute it in, okay. Then what you have, T of E1 is equal to V, which is 1, 0, 0 minus 2 by 3 times inner product of V and N. Okay, so inner product of E1 times the normal of the plane that we have, which is nothing but 1, 1, 1. Okay, times 1, 1, 1. Okay, which is equal to 1, 0, 0 minus 2 by 3 inner product is nothing but 1 here times 1, 1, 1. So this is rendered as 1, 1, 1. So this becomes 2 by 3 times 2 by 3. Okay, so 2 by 3, 2 by 3, 2 by 3. Okay, and then you get what, minus 1 by 3. Oh no, 1 by 3. You get 1 by 3. Yeah, 1 by 3 minus 2 by 3 minus 2 by 3. Good. 1 by 3 minus 2 by 3 minus 2 by 3. Oh, okay, that's good. Pretty quick. So now you do T of E2. Okay. So you got minus 2 by 3, 1 by 3, 2 by 3. Right. Okay, let's check that out. T of E2 is 0, 1, 0 minus 2 by 3 times inner product of 0, 1, 0 and 1, 1, 1 and which is and times 1, 1, 1. Okay, which is equal to 0, 1, 0 minus 2 by 3, and this inner product becomes 1 again. Okay, I think anyhow the inner product is going to be 1, so we don't need to calculate it further anymore, which is equal to 0, 1, 0 minus 2 by 3, 2 by 3, 2 by 3. Okay, and here you get minus 2 by 3, 1 by 3 minus 2 by 3. Okay, let's see your answer. Minus 2 by 3, 1 by 3 minus 2 by 3. Correct, yeah, good. And T of E3 equals 0, 0, 1 minus 2 by 3. Okay, we don't need to write the inner product. It's going to get to 1 and 1, 1, 1. So it becomes 2 by 3, 2 by 3, 2 by 3. So it simply means this is minus 2 by 3, minus 2 by 3, and this is 1 by 3. Okay. Okay, good. Now, all you need to do now is, okay, your target matrix, the linear transformation T, okay, which is a 3 by 3 matrix. You can just write it as a column vector E1, E2, E3. Now this is so general. This is like so general and beautiful that now you've captured the entire reflection using a single adjacency matrix. Oh, I'm bringing in at what using a single transformation matrix. So put E1 here. I'll take reference from the chat so that I don't need to change the page. 1 by 3.
Sir, you meant T of E1, right? In those columns, T of E1, T of E2, and T of E3.
Sorry. Yeah. T of E1, good. T of E2 and T of E3. Good. Yeah. Minus 2 by 3. Minus 2 by 3. Okay, so you've given two E1s. Now I'm confused. Okay, which one is it?
No. So the later one is TE3 actually. So I was copy pasting the results and.
Oh, okay. 1 by 3 minus
That's
2
why
by 3 minus 2 by 3. 1 by 3 minus 2 by. Okay. Yeah. No, I didn't want to keep
1 by 3
changing
appears
pages,
in
so
the
I was
diagonal.
looking at the chat.
Okay.
Okay.
Sorry. 1 by 3 appears in the diagonal, and all other elements are minus 2 by
1
3.
by 3. Okay. It's 2 by 3. And everything else is, yeah. It's like 2 by 3 minus 2 by 3. 1 by 3. Now. Okay, it's 12. It's 7:49. Okay. See, this is the thing now. This matrix represents reflection across. Okay. This represents reflection across plane x plus y plus z equals 0. Okay, good. Now, here's the next question. It says, it's a vague question, but still, come up with a scheme to verify that T is indeed a reflection. So can you guys think of this, like, is there a quick verification to actually see that T is actually a reflection?
So for a quick reflection, can midpoint be used? Like that. I will take any point.
Okay.
Yeah. So I will take any point. I'll take the and I will know what are the operations on that point. Like T of V, I will quickly find it because I already have T, and I'll show that the midpoint lies on the line x plus y plus z equal to 0. So I'll show that yeah, it's indeed a reflection.
Okay. I mean, can you find? Okay. I mean, you can. You mean to say that find the midpoint? Not find the midpoint. You mean to say that the midpoint will always lie on x plus y plus z equals 0?
Yeah, because I think that's a very intuitive property for reflection to me.
Okay, that may be possible. How will you show it? That's the question. You need to take like two arbitrary vectors and then say one is mapped through T and then compute the
no, actually I'm thinking about just a point. Okay, let's take any x comma y comma z point, or let's say u v w point. I'll apply T on that particular point.
Sorry, yeah, I didn't mean two arbitrary vectors. I meant one arbitrary vector.
Oh, okay.
And then apply T. Then you get two vectors.
So I will get the end result. Yeah, and I will show that the midpoint lies on. Yeah, and that should zero take.
Okay. Yeah. Before that, I would like to ask others also.
Yeah, sure.
Is there any idea that you guys are having to check whether it's a reflection? And mind you, okay. So yeah, Rohan, I'm just asking whether it's a reflection. It need not. I'm not asking whether it's a reflection across x plus y plus z. Okay, so I'm relaxing the condition. Okay, so others, it's also I'm going to ask. Yeah, Kishore.
See, with respect to 2D, in two-dimensional, what I can say is interchange of the coordinates. That can quick reference. We can say there's a reflection. Let us suppose it's a 2, 0 coordinate can be 0, 2, and if it is totally the direction change, then probably the minus sign will indicate that.
Okay. But that is for x equals minus y. No, that this. But what I'm saying is don't concentrate on checking whether it's a reflection across x plus y plus z or x equals minus y. I'm just saying check whether it's a reflection. It could be whatever plane, across whatever plane, across whatever line, whatever. Okay, you just need to check whether the matrix is doing a reflection. It's a very relaxed condition. You don't need to go through. Yeah, well,
if you relax
one
it to
of the coordinate should become minus. I mean, all other if a matrix, if a linear transformation keeps all other things intact except one.
Okay.
And one thing keeps the value, but then becomes minus. So then it would be a reflection.
Okay. But that's not an absolute check.
So I have one point.
Yeah.
So if you relax that condition that x plus y plus z equal to 0 plane, it's not that plane, it's any plane, and you want to take a reflection. Yeah. So let's check.
And I don't need to. And I'm not saying that you should check that whether it's a reflection across that plane only. Okay. Only check whether the matrix is a reflection matrix. You got what I mean, no?
Oh yeah, I got you. But so then I'm wondering what are the properties of a reflection matrix has? Like I'm not getting exactly that thing. So
yeah, I mean, see, the property it has is of course that that's a. So if you look at it, so that the answer will lie there if you look at the reflection carefully. Okay. So if you reflect a point across another point, okay. First of all,
okay, I got you. T square would be I. So
okay.
You double take the reflection,
what?
you'll end up. So T square equal to I, you'll end up in the same place.
Not
so
I.
Twice. It should be I.
Okay. Yeah, T square is equal to I. Yeah, I is also an accept. Yeah, that's perfectly fine. Yeah.
Oh, nice. Yeah.
Okay, so so what you do is, okay, this is V and this is T of V. This is the reflection, right? All you do is you apply T once again. So this is like related to a question, Goel, you were asking, right? Getting back to a point.
That's a very nice.
Yes. So if you apply a transformation to vector V once, and then you apply the same transformation back, it means you're just getting front and back, right? And therefore, if you do T square, okay, that should be identity, because what you are saying is T square times V is equal to V, and you can like right multiply, and then you can just get this as identity, right? So yeah, that's the answer. Good.
Sir,
thanks, man.
But if we can suppose in general someone says T square equal to I, will it always mean that T square is a reflection matrix?
That's a good question. Check it out. Okay, I would recommend you to look at you sort of draw a grid, okay, and look at how the transformations are affected, how transformations affect grid. Okay, check that out, and you will get your answer why this is correct. Okay, so because you really see that it can't be that. I mean, even if you're doing something like skewed, there is some kind of. I'm not going to go too much in depth with this, but check it out. Okay, why this is correct. Okay. Okay. So now. You can verify this. Okay, so this part I can't. I mean, it will take some time. So do a square of this, and then you'll see that it's reflection. Okay. Now,
sure, sir.
Yeah. Compute the eigenvalues and eigenvectors of the matrix representing T. Okay. So this is going to be a bit tedious. So 1 by 3, 2 by 3, 2 by 3. 2 by 3, 1 by 3, 2 by 3, and 2 by 3, 2 by 3, 1 by 3. Okay.
Can't we multiply everything by 3 so that we get rid of these fractional values?
We can use the fact that T square equal to I. So Tx equal to lambda x, and we'll apply T again.
Just one moment, okay? I'll do just 1 moment. I'll charge. Okay?
Sure.
So my battery is about to run out. Okay, who's saying? Okay, yeah, Goel, you were saying, can you multiply with 3? Okay, yeah, that's a good decision. It will help us. Yeah.
Sir,
Yeah, Rohan.
can we use that t square equal to I thing, which is just now you showed us, and that will give me lambda equal to plus minus 1. So reflection matrix can have only eigenvalues plus minus 1.
So what you are saying is
Ex equal to lambda x.
equals to t square, t equals lambda x, that's fine.
Right. X equal to lambda x.
V equals lambda
Yeah.
v, and then what you are
Apply
saying
t
is
once more. Yeah.
t and
Lambda
then
into tv.
lambda into tv. Okay.
T square equal to I. So in the left hand side, I have
Yeah.
only v.
This is I. So this is IV.
In the right hand side, I have lambda into lambda times v, because tv equal to lambda v again.
Lambda square v.
Right. So
that's,
lambda
yeah,
square
that's,
equal to plus minus.
that's a nice reduction. Good. Yeah, nice one.
I think Goyal or someone said that that t square that applying tv again lambda v. So I took his concept actually. In the previous problem, someone mentioned that.
Oh, okay, nice. Okay, good. Yeah, great. So now lambda is 1 and minus. But yeah, let's also see why that is correct. Okay, so you have determinant again. You need to find, right. So determinant of
Excuse
1
me, sir.
minus. Yes, sir.
Excuse me, sir.
Yeah.
Sir, that what expression you have written lambda square v
Huh.
to lambda v
Oh.
value will be
Yeah.
again tv value will be again lambda v. So it will be lambda lambda square v.
Lambda square.
Right.
Correct,
Okay.
no?
Right. Got it. Sir.
Oh, okay, great, good. So this is 1 0 0 0. This is 1 minus 1 0, and this is also 0 0 1 minus lambda. Oops. Is there a mistake here? Oh, okay, because this is lambda square. Okay, good. Equals 0. Right. Determinant should be equal to 0, and then this is nothing but product of all three elements in the diagonal, and by property of determinant, and this implies 1 minus lambda square is 0, and lambda square is plus minus 1. Okay.
Sir, why the determinant thing? I missed the part.
Why the determinant came? So how do you compute? So like the previous question. Okay. How do you compute? You do this, no? Determinant of
Okay.
you get it, no? So a minus lambda.
I think I'll be using. Okay. Right. I actually thought we'll bring everything to one side. So we'll write lambda square minus 1 into v equal to 0. And since v is non-zero, so lambda square has to be 1.
You can do that. I'm just standardizing the process.
Okay.
Okay. Yeah. So yeah. Okay. So this you get lambda square equals plus minus 1.
No, lambda equal to plus minus 1.
Sorry, lambda equals to, good, thanks Satinder. Yeah, good. So lambda equals plus minus 1. So now you need to calculate the eigenvectors. So what's the time? Okay, it's already 8, but I think it's kind of important to see this. Should we have okay, let's do it in like 5 minutes. Okay, so if lambda is equal to 1, let's substitute it here. Okay, in the equations, 1 by 3, 2 by 3, 2 by 3. So so what we were saying is determinant, not determinant, AV, okay, sorry, TV minus TV equals lambda V. So you have TV minus lambda I.
Do we need to find eigenvector for this particular problem or for any?
Yeah. You need to. That's
okay.
The eigen. That is a question, no? Actually, it's a bit of a drag, but actually I wanted to do this to get a more conceptual understanding. But it's okay. We don't have very much time. Okay, so we won't compute the eigenvectors, but okay. Let's just.
You can show us the.
Huh?
You can show us that T once the matrix of T. You can show us and give us 2 or 3 minutes. We can try and we can give you the answer in 2-3 minutes.
Okay, I'm not sure because it's almost time. Okay, sure,
Oh,
sure.
okay.
Okay.
No worry then.
I can give like 1 minute, but I don't think that's possible in 1 minute. It'll take some time. Okay.
Let's try, sir, in 1 minute.
Yeah.
Let's try it
Okay.
in 1 minute.
You guys can try in 1 minute. Okay. Okay, I'll give you guys 1 minute. So, but no more than that.
Okay, sir.
Okay.
Show us T once. That
Oh yeah,
matrix.
sure. So this is T.
Right. Is it T or minus 2/3 should be there, no? Like minus is where there?
Is it? Yeah, sorry.
Yeah.
Okay. I mean, I'll also do it parallelly. Okay. This should be X, Y, Z. Or V1, V2, V3, let's say. Okay.
Yes, sir. 2 eigenvectors, sir. I can tell
Okay.
you 2 eigenvectors.
Yeah, so when lambda equals 1, let's see first.
Yeah, right.
When lambda
equal to
equals 1,
and
then
2 eigenvectors are minus 1, 1, 0,
minus 1, 1, 0.
and minus 1, 0, 1.
Okay, just give me one moment. Okay.
Sure.
Okay, it's okay. I'll call back now. Yeah.
Okay.
Yeah, so
minus 1, 1, 0, and minus 1, 0, 1. The next one is minus 1, 0, 1.
0, 1. Okay, good. Okay.
Yeah, and lambda equal to minus 1. I'm finding it. Just give me 30 seconds.
Yeah. Lambda equals minus 1.
Yeah, I'm finding that. Just
okay. You should be getting one vector, eigenvector.
Yeah, right. Free variable is 1 only, I think.
Yeah, did you get?
Yes, sir. 1, 1, 1.
1, 1, 1. Okay, good.
Yeah.
Yes. Okay, now let's just quickly wrap this up. So look at the plane, okay? So what kind of transformations actually happen? Look at that, okay? If you so does it question is, does the transformation preserve direction? Okay, so if you have this as the plane, and in what kind of points does it preserve direction? What happens if I reflect across here? Then of course the problem is the direction is changed now. But if you look at, okay, let's simplify it in the 2D case. Okay, 2D case, when is direction not changed on reflecting? And first of all, you might say, oh, it's a strange question to ask, because you know, the direction, it may be reversed in, you know, arbitrary ways. But if you look at this, let's plot this 1 1 1. Okay, what will it look like? That is the first kind of point you have. Okay, 1 comma 1 comma 1, and then you look at this point. Okay, if you reflect it across this guy, okay, you will get somewhere here. If you reflect it through here, you'll reach somewhere here. And 1 comma 1 comma 1 means anything 2 comma 2 comma 2, you'll get somewhere here. 3 comma 3 comma 3, you'll get somewhere here. The idea is that, okay, the idea is that 1 comma 1 comma 1, okay, just because I've drawn the plane ulta, okay, but 1 comma 1 should be looking like this in that ulta direction. Will go here. Notice that this has reversed, the direction has reversed, but the axis is still same. And if I reflect this point here, direction, the axis is still same, but the direction has flipped. So this is what a negative direction represents. And the 1, what does it represent? The length of the vectors are same. Same thing is happening here. 1 comma 1 comma 1 will be lying across this. Okay, again, the plane I've drawn is ulta to what it actually is. So this is actually minus 1 comma minus 1 comma 1 comma 1, whatever. Okay, you get it, right? The length is preserved when you reflect. This length is same as this length, and the direction is reversed. That's why that is what the eigenvalue represents. Lambda equals minus 1. Now what does 1 comma 1 comma 1 represent? It represents all those vectors which lie on this axis. Now what is the second vector then? What does the second vector really do? If you observe the second vector, okay, it's too late now, I'm not going to plot it on the graph, but if you observe these two lines when lambda equals 1, they will lie exactly on the plane. They'll be like the basis vectors for that particular plane. They'll lie exactly on the plane. Using their linear combination, you can get anywhere on the plane. But what does lambda equals 1 mean? First of all, the length is not changed, and secondly, the direction is not changed. So these are the points which on reflection will get the same thing, which intuitively also makes sense, right? Which intuitively also makes sense that only those vectors are not changed which lie on the same plane. And that is represented by this lambda equals 1 and these eigenvectors. And lambda equals minus 1 represents that the direction has changed, but the length has not changed. Okay, that's what lambda equals minus 1 represents. And that is represented by this particular line 1. Okay, I just wanted to build that concept and end the session. Okay, I hope that is clear.
Yes, sir.
Okay, great. Okay, good then. I think we can stop the session now. Okay, we'll meet in the next problem solving session next week, next Tuesday. Is that fine?
Yes, sir. So next Tuesday on the same time?
Yeah, same time, Tuesdays.
Okay. Sure.
And which topics shall we cover in the next week?
I think vector spaces. I'm not totally sure. I think vector spaces. That's what I think. But don't rely on that. Check out the website once again. Yeah.
Okay, sure.
Okay.
Thank you so much. Good night. Bye.
Okay. Thank you. Good night.
Hello.
Thank you very
Yeah,
much, sir.
Satinder.
Excuse me, sir. Sir, can I see the solution again from the beginning? Actually, there was a network problem from my side, so I couldn't see the solution. Just this question solution, can I see from beginning? This question.
See meaning you just want to see the notes or
Just solution I want to see. Quick
Okay.
recap. That.
Oh, okay. Okay. I this question is pretty long, Satinder. Is it okay if I tell you to check out the recording? Huh, Satinder?
I want to see the solution. I want to just see the solution just for this.
You
Just
want
roll it. I'll just.
you want a recap? That's what you mean?
No, I don't want recap. Just I want to see the solution.
Oh, okay.
How we
Okay.
have got the matrix. That one.
I think he is asking for the notes. The notes will help him, I think.
Oh, okay,
if
okay,
it's
okay, okay.
great for you, I think you can send him the notes and.
Yeah. Just one moment. So, okay. Anyway, Satinder, I'll be uploading the notes on the drive also. But which part ABC do you want to see the solution?
Just I want to see the T transformation matrix that how we have
Okay,
got
okay,
that part.
okay. That part. Okay. Okay. We used this formula, okay, that we saw in the previous sessions, and with this formula we got for a general V, not a particular V, and then we applied the basis vectors there, and we used that as a columns, and then we got the transformation.
Okay, sir, got it, sir. Got it. I've seen that one.
Okay, great. Okay, thank you then.
Okay, thank you, sir. Good night,
Okay,
sir.
thank you. Good night. Okay.
Thank you very much, sir. Yeah.
Okay, thank you. Okay.
Yeah.
Good night. Thank you. Okay, thank you. Stop. Yeah, Mr. Shivkumar, that's fine, no? Hello? Hello? I'm ending the meet. Is that fine? Hello? Okay, I'll be ending the meet. Okay?